So you remember that in the last class we discussed why we were interested in current algebras, and then we decided that we had discussed SU2 current algebras in great detail, and we decided we would get more serious about it. And part of getting more serious about it was to try to understand Lie algebras for more general groups. Okay, so we had started our discussion. I'll just remind you of the main elements of it. Suppose we've got some generators JA. These are a basis for our Lie algebra. Okay, then we found a maximal commuting set of generators. We called those HI. Those were the Cartan elements. Okay, our Lie algebra had an inner product which you could think of as like a trace. Okay, you can think of a trace in some representation, let's say adjoint representation with some normalization. And so we chose our normalization such that trace HI Hj was equal to delta Hj. I mean, we chose an orthogonal basis, and we chose an orthogonal basis inside this trace. That's what I'm saying. Okay, great. Then we discussed that in addition to so these are the Cartan elements, and the number I runs from 1 to I think what's called the rank of the matrix of the Lie algebra. Okay, there's another integer in the game which is the dimension of the Lie algebra. Okay, and the rank and dimension, of course, are integers. In general, the dimension is significantly larger than the rank. For instance, in SUN, the Lie algebra SUN, the dimension is n square minus 1, because that's the number of independent generators, but the rank is n minus 1. So if n is large, the dimension is much larger than the rank. Okay. Then we discussed the following. We discussed the form of the commutation relations between these guys. You remember we had that Hi J, of course, was equal to 0 because we chose these to be commuting elements. And when we found we put all operators into pairs, E alpha I and E minus alpha I, or E alpha I Dagger, which had equal and opposite eigenvalues under H. And we defined Hi, the eigenvalues of E, whatever they are, we call them alpha I. So alpha I, E alpha I. Okay, so far so good. And we're labeling these E's by their eigenvalues under H. These are the labels for these, for these E's. That's what that E alpha I means. Okay, and right at the end of the last class, we started trying to understand what we could say about E alpha I, E minus alpha I. Okay, so let's now get a bit more serious than we were last class. Of course, given these roots, these things are called roots. Okay, these non-zero, non-commuting elements of Lie algebras are called roots. And given these, if I've defined the root by an eigenvalue relation, but eigenvalue relations being a linear relation invariant under scaling. So I have freedom to choose the normalization of E alpha I however I want. I'm going to make a choice that will be convenient for me. Okay, I'm going to choose to normalize these so that the trace or inner product, I'll always write trace, but it's inner product, is E alpha I, E alpha minus alpha I. This is equal to 2 by mod alpha I square. So what does mod alpha I square mean? Mod alpha I square is just sum over alpha I, or sum over all I. It's Euclidean dot product. If you were a mathematician, you would go through all kinds of convolutions. Because you see, alphas are not elements of the Lie algebra. It's elements of the dual space. You see, because you take an H and you act on a given root, and that gives you a number associated with that root. Okay, so that number is a number given a root. It's a way of getting a number out of H. The number is alpha I. Okay, so if you have a rule that gives you a linear rule that gives you a number out of an element, that rule is called an element of the dual space. So if you look at a mathematical text, they will very carefully distinguish elements of the dual vector, the dual Cartan space, which is this root space, okay, and the and elements of the Cartan space itself. But in a space that has a natural inner product, and working in a basis where the inner product is delta Ij, okay, there is a completely canonical, elements of dual space and ordinary space are just related by lowering and raising indices. Because if you've got a lower index as an element of your space, you have an upper index, you can contrast and get a number. But since lowering and raising is trivial, since our metric was delta Ij on H, there is no need to be so careful, and we will tend not to be. Okay, so for us, this root space, the space of roots, the space in which these alpha i's live, is basically the same as the space in which the Cartan elements live. Okay, just because if you were working with a more general kind of system, something with a degenerate inner product, or something like maybe not positive definite, some non-compact Lie group, you'd have to be much more careful. Okay, it would be like the difference between upper and lower in Minkowski space, where you have to be careful because time changes sign. The time guy changes sign. But here we don't have to, so we won't bother. Okay, excellent. So coming back, as a metric in the more precisely in inner product. No. Yeah, something that allows you to raise a lower index. Okay, yeah. So excellent. So we wanted to find what this guy is. Okay, now because this guy under each hi, this guy has weight, has eigenvalue alpha I. That guy has eigenvalue minus alpha I. Eigenvalues of hi add up, as you can check from Jacobi identity. Okay, so this quantity has zero eigenvalue under all hi's. But the only quantities that have zero eigenvalues under all hi's are those that commute with all hi's, and therefore linear combinations of h's themselves. Okay, and so we have that E alpha I, E minus alpha I is equal to sum over Ci, I'm not even writing the sum, Ci Hi. Okay, now in some vector space, if you've got an expression like some vector is a linear combination of basis elements, okay, if you've got an expression that a vector is a linear combination of basis elements, you want a formula to read off the coefficient. Well, what do? Well, you take the inner product with the dual basis element, but we're not being so careful, so we take the inner product with the basis element. Okay, so using the fact that Hij inner product is 1, we find a formula for Ci. Ci is equal to trace of Hi times E alpha I, E alpha j. Right? So we've got this formula. Okay, so far so good. What good has it done us? It's some abstract formula, doesn't look like we've gained anything. But we gain something by using cyclicity of the trace. So let's just open this guy out. So this is trace of Hi E, let's make this Hm, because this In, that I needn't be the same, right? Cm is this. So we have trace Hm, E alpha I, E minus alpha I, minus the other way around, so Hm, E minus alpha I, E alpha I. Okay, not bad. Now what we're going to do is to use the cyclicity of the trace. We can use on either one. Let's say we use it on this guy. So we take this guy and cycle it around so that the alpha I will come to the left here. So this, because of cyclicity of the trace, we can as well write as E alpha I HM E minus alpha I. Right? No difference. And now what we've done is rearrange the commutator. The earlier expression was commutator of the two E's, which we did not know. But now we've got a commutator of HM with E alpha I, which we do know. So let's write it. So we get trace of HM with E alpha I, E minus alpha I. That's just from by definition. Right? Now, HM with E alpha I, okay, is alpha M E alpha I. So this is equal to the trace of this. Okay? And this quantity, so now this is just a number. This quantity by that relation then is 2 by mod alpha I square. Okay? So we have alpha m, 2 alpha m divided by mod alpha square, whichever the alpha is. Okay, I kept saying alpha I, but whatever that, I won't, whatever the alpha we're dealing with, I won't say. Okay, so whatever, the alpha has really two labels, right? There's which root, that's the ith, and which element, which h. Okay, really we should be going through with all of that, but I've just taken one of them, okay, so that we don't confuse ourselves. Okay, and so we've got this guy. So that's the formula for Cm. So Cm was equal to this, and therefore we get we find that E alpha I, E minus alpha I is equal to 2 alpha m divided by mod alpha square Hm, the summation implied. Okay? So we've discovered the commutation relation between two roots, I mean a root and its anti-root, a root and its Hermitian conjugate. Okay, just using very simple manipulations. Okay, great. So we almost know everything about the commutation relations in the group. We know about what happens with h with h, that's 0. We know what happens with h with a root, that gives you these alphas.
But
okay.
This is the same thing like J plus and J minus.
Absolutely. It's very similar to J plus and J minus. So since you've brought it up, let's go. Now which way does it go? Which way does it go? Which one gives? Let's work it out. J plus and J minus gives 2jz? Yeah, let's just check that. So J plus was Jx plus Ijy. J minus was Jx minus Ijy. And you take the commutation relation of these, you get Jx, Jy, which is Ijz. So minus I to I, yeah. So this gives 2jz. Because each of the two. Right. Right. And therefore, do I still have a mic? Okay, hopefully. Okay, yeah. So therefore, as was pointed out, E alpha I, if we think of this as J plus, let's call it just E alpha, associated with any root. Okay, we can think of this E alphas as J plus, E minus alpha as J minus, provided we identify Jz as alpha dot h by mod alpha square. So we even have the 2 nicely sticking out. Okay? Excellent. And in particular, in the case of SU2, there's only one root pair, which is J plus and J minus itself. Alpha is plus 1 for J plus, minus 1 for J minus. Okay? And in that case, we will get 1 by 1. I mean, in that notation, 1. Yeah. So we get just 2 times Jz as we had started. Please.
So for SUN, it's evident.
SU?
Let's say SUN.
SUN, yes.
It's evident non-Cartan generators will be even number.
Ha.
Is it the case for any?
It's the case for every, Lie group of the type we're considering, whatever, semi-simple, whatever, non-semi, not without extra U1 factors.
Why it turns out n square minus n.
N into n minus 1.
Exactly. So there, as you say, it's obvious, okay? But in every case, it's true.
Why is that?
Why? You say, okay, good. You see, we've seen that every root comes in pairs. The only roots that don't come in pairs are those that have zero eigenvalue. Yes. Sorry. So your question was subtracting out the Cartan. Why do they come? Why are they even? Because they come in pairs. Because of Hermitian conjugation. You see.
But there exists minus.
Yeah. For every root, suppose I take a root, I take its dagger. It has minus the root value. The only guy, so therefore roots come in pairs unless they have zero alphas.
Or the dagger is equal to itself.
No, but they have different eigenvalues. So they cannot be equal to itself. Right? Things with, yeah. Okay, and the dagger is equal to self in the case where the root eigenvalue is zero. So this is just simple proof. Okay, great. Other questions or comments? Excellent.
For
Please.
each alpha, there existed corresponding asymptotic channel.
Yeah, and we'll be using that extensively. Yeah, please. What? No two-dimensional Lie algebras of the sort. Of course, there are some words associated. No semi-simple, whatever. If you take two U1s, it's a two-dimensional Lie algebra.
Yes, but of course, non-abelian.
Non-abelian ones that don't have U1 factors, right? Yeah, no two-dimensional. Yes, no two-dimensional non-abelian Lie algebra. Right? The smallest Lie algebra is SU2. You're looking very worried. Tell me what you're worrying about.
No, I can just define a Lie algebra. Suppose generated by J1 and J2.
Okay.
With J1 coming.
Let's try. J1 commutator J2 as defined as J1. Okay. This is a valid Lie algebra, two-dimensional, but it won't have some of these properties. Okay, so let's see. What? Yeah, it will. So let's try to understand what this is. This is, let's find a simple kind of, it's like number operator and a dagger. Okay? Now let's see. First, in that case, suppose you had a number operator and a dagger. This is equal to whatever a dagger. Okay? In the just one second. In that case, the hermiticity was n dagger, and a dagger went to a. Okay, but you see, the thing is this: if you've got this compact Lie algebra with an inner product that is of the form that it will allow you to just set everything +1 +1. I don't think you will ever be able to find.
You are claiming that the inner product is either degenerate
Or that you will have to increase the algebra to. Yeah. Think harder. Try to come up with an example.
Here I think also Jacobi will not work.
Jacobi will not work. This will work because it's this. Yeah. It's implemented inside a harmonic oscillator, right? So there's no problem with it. One thing about it is, firstly, harmonic oscillators have these infinite dimensional generalizations. So from the representations from the point of view of a Lie algebra, it will be non-compact. Second thing about it is, in the context of the harmonic oscillator, you would have to include also the A. Okay? One of these two things, or maybe both, will always hit you. Okay, yeah. Sorry. Yeah. Okay. Fine. Let's keep going. Okay. So we've got this the implementation of the commutation rules, we found H with H, we found H with E, and we found E with its own dagger. But we've not in general found E with the other E's. Okay? So, what can we say about E alpha I with E alpha j? Well, let's see. Either, let's look at the weights of this guy. This guy under H is the sum of the weights alpha I and alpha j. Okay? Charges just add. Okay? So either there is a root in the theory with weights alpha I plus alpha j, or there is not. If in your Lie algebra there was if in your Lie algebra there was no root with weights alpha I plus alpha j, this has got to be 0. Okay? If there is a root, this will be some nij, not necessarily at this point integer, just some, let's call it aij, so that you don't get aij times E alpha I plus alpha j. Okay? And finding the program of classifying Lie algebras is the program of finding all possible allowed aij's. If you can find them all, such as Jacobi identity, everything else that you want, you've, compactness, blah, 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 all of that, you've classified all the algebras. Okay? Great. So that classification should also tell you what alphas are allowed. Okay, and we'll see some hints about it. We won't go through the whole discussion of this. This is one, in my opinion, one of the great pieces of whatever century, 20th century, I suppose, mathematics. Why, by the way, is this so important? I mean, it may not be so great for the mathematicians, I don't know. But why is it so important? So important because Lie algebras are symmetries in physics. So if you give a classification of all Lie algebras with certain properties, you have given a classification of all symmetries, continuous symmetries with those properties. And to have a finite list, or not finite, but an innumerable list of all possibly allowed symmetries is a fantastic thing. Right? You come back knowing if your system has a continuous symmetry which has certain properties, a compact, blah, 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 okay, of this sort, it must be one of these lists. Also, as you know, these same Lie algebras appear when we look at gauge theories, because gauge theories start with symmetries and then gauge them. And there, this compactness, blah, 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 is totally key, because it determines the unitarity of the theory. If there wasn't this nice positive definite inner product, gauge theory would not be unitary. Okay, so it's totally key. So it also gives you a classification of all allowed gauge groups in gauge theories. So it's totally remarkable that you can do some mathematical mumbo jumbo and come up with that list. This is one of the things the mathematicians are good at. Once in a while they produce these totally remarkable results, which, for physicists are totally remarkable. This is one example. Okay. By the way, just as a side comment, what will be in the 21st century what Lie algebras were to the 20th century, assuming they were in the 20th century? Can't swear they weren't in the 19th century. Probably not. Okay. Well, of course, nobody knows, right? But let's make one conjecture. One conjecture would be the classification of all fixed points of the renormalization group. Unitary. Classification of all unitary fixed points of the renormalization group is a problem that feels like that. Why is it a problem that feels like it? You see, just like Lie algebras classified all possible symmetries, fixed points of the renormalization group classify all possible somethings, all possible conformal field theories. Now, conformal field theories are the mothers of all field theories, because every quantum field theory is described by renormalization group flow away from a conformal field theory. So in some sense, it also classifies all possible classification of these conformal field theories plus knowledge of their relevant operators gives you a classification of all possible quantum field theories. So it would be an even more remarkable result. The set of all allowed quantum field theories in the world would be totally fantastic to know. And people are, with very limited success so far, but people are trying to pursue this classification through this program called the conformal bootstrap. And you know, at the heart of the classification of Lie algebras lay the Jacobi identity. You know, that's where much of the meat, what we've been discussing, comes. And very roughly speaking, you can see that Jacobi identity should be somewhat constraining. Because what? Because, you know, well, we come to it. We defined the structure constants last time, right? This FABC. So these FABCs are 3-index objects. But, so what you're trying to do is to classify all possible 3-index objects. Okay? But if we work out the Jacobi identity itself in the adjoint representation, we will actually have an equation with 5 indices. Because we have to choose which 3 generators we put, and then there are 2 indices left over, which is the matrix indices. So Jacobi identity in the adjoint representation is like a 5-index equation for a 3-index object. So if the number of indices becomes the range of which the indices vary becomes very large, this is extremely constraining. That's one way of thinking of why we don't have families of these, you know, large numbers of families of these theories, right? I'm oversimplifying because you need this compactness, blah, 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 but okay, this is part of that. In the same way, conformal field theories, as you guys know, the attempt to classify conformal field theories, is through this conformal bootstrap. And the conformal bootstrap, once again, tells you that if you take a 4-point function, you fuse I with j and m with n. Okay? You do it through this channel, and you do it through that channel, you get the same answer. So from this point of view, apart from the scaling dimensions of the object, the main data is these 3-point functions. So once again, some 3-index object, some 3-index object data. And at least you can see that the equations are 4 indices because they depend on the 4 external operators. Actually 5, because there's one equation for every channel of flow. So once again, it's 5 index equations for 3-index objects, which just immediately suggests. Now, of course, you have to be a bit careful because the number of indices now is not some finite number, runs to infinity. But still, it immediately suggests there can't be too many conformal field theories. Certainly when we put all this unitarity wisdom. And that's in line with however many, 50 years, 70 years of study. We also find from other considerations there aren't too many conformal field theories. So the study of conformal field theory is very similar to the study of Lie algebra in some vague sense. Much more difficult, but what we're looking for is the same kind of brilliant insight that allowed one to classify all Lie algebras. Maybe someone in this room will classify all fixed points of the renormalization group, let's say 4 dimensions. What an accomplishment that will be. Because it would give you the list of all possible unitary quantum field theories. You know, it would be used forevermore. That's why I think this is one grand goal it would be one grand outcome of our line of study.
Will this classification program be dimensional?
Oh yes, we're sure of that. For instance, superconformal field theories don't exist in above 6 dimensions. Whereas they do exist in 4 dimensions and 6 dimensions. So certainly it will be dimensional.
What is the reason? Is the algebra doesn't use
Just that there does not exist a superconformal algebra. Yeah, above 6 dimensions.
Above 6.
Yeah. So the same kind of classification we're talking about here can be done for superconformal algebras. And this was done, and you get a finite list. None of them include something that includes both the conformal algebra and has fermionic elements that transform as spinors of the conformal algebra in higher than 6 dimensions. In my supersymmetry class, I explained this fact. So if you're interested, that's video somewhere on YouTube. Okay, great. Excellent. So that was just motivation. That was just, I mean, all these words are easy to say. But it really feels to me like it's a similar problem. And really feels to me like it's kind of thing where, like, we do a lot of physics stuff, right? But there's some value in doing some crazy mathematics once in a while, like this Lie algebra stuff. And maybe it'll come from some crazy mathematical idea. That stuff. Maybe it's that kind of problem. Or maybe not, I don't know. Okay, great. Great. So let's keep going. The next thing I want to do is, well, we want to discuss lots of things about these Lie algebras. It'll probably be this lecture and the next one, then one or two more for affine extensions of Lie algebras when we get back to physics. So please bear with me. Okay. Why are we doing this? First, because we want to, when we study Kac-Moody algebras in higher dimensions, we keep coming across various quantities like this dual Coxeter number. Various things that will appear. You have to know what they mean. Second, because the mathematical structure of these affine extensions of Lie algebra is not very different from Lie algebra. So even if you're only interested in SUN, affine Lie algebras, which oftentimes you're only interested in simple things, just to understand the affine extension in this language somehow has some value. Okay, so let's be patient, put up with this mathematical nonsense for a while. Okay, then we come back to physics. 3-4 lectures, maybe 3 lectures. Okay. The next thing I wanted to discuss was weights. Okay, so far we've been talking about the algebra itself. Okay, I'm not going to go through a classification of how you find all of these. We'll have some hints about it and I'll tell you more about it. I'm not going to go through a systematic classification, but I'll tell you more about it. But before that, before we come back to classifying all possible Lie algebras, it's nice because it's useful even for that other program. Okay, it's and certainly it's useful for all kinds of physics. It's nice to start thinking about representations of this Lie algebra. Okay, so what's a representation of this Lie algebra? Well, it's some matrix that implements the commutation relation of the algebra. Right? Like in SU2, it's these 2j plus 1 times 2j plus 1 dimensional matrices. And this stuff, Okay, some matrix representation of this thing. So now suppose we've got some objects that transform in this under the symmetry. Okay, so we've got some weights which we call some vectors which transform under this symmetry. How are we going to label the vectors? Well, as always, we label them by the eigenvalues under a maximal commuting set of operators. So we label them by the eigenvalues under the HIs. Okay, so let a vector that is that has eigenvalues lambda I, lambda 1 under h1, lambda 2 under h2, lambda n under hn, let it be called lambda. Clear enough?
So in particular, these are basically this hypercharge isospeeds.
Hypercharge, this is SU3? Yes. Okay, probably. Okay, yes. Okay, yeah, fine. Yeah, SU3 clearly has two Cartans, and you can choose some linear combinations and give them a name. I know nothing about hypercharge and whatever, but okay.
One is called hypercharge, one is called isospheres.
Excellent. Okay. Okay. Fine. Okay. So we've got this weight space with eigenvalues under hi. So but this definition of lambda is hm lambda I. I should really put brackets. I often won't. Is equal to lambda m lambda I. Clear enough, right? Okay, so it has weight lambda m under the Cartan lambda. Okay. Now, what can we say about these weights? Okay, now we're going to do something that you suggested. That is this. Since we have that E alpha, E minus alpha is equal to 2 alpha m h m by alpha square. Since this is true, and we've already seen that this is the same commutation relation as j plus j minus equals to jz when we identify j plus with E alpha, j minus with E minus alpha, and jz with alpha dot h divided by alpha square. Okay? Since we have this, we see that every Lie algebra in particular has several SU2 subalgebras. Because if you take the three generators, E alpha, E minus alpha, and this particular linear combination of H's, the commutation relation between them closes and gives you that of SU2. Okay? I'm not saying that it's like a direct product. It's not true that these SU2s don't talk to things outside. They do. But that's not important for what we want to say. Between the three of them, they implement an SU2 algebra. Now, in normal SU2, J plus and J minus are Hermitian conjugates of each other. But that same thing is true here. E alpha and E minus alpha are Hermitian conjugates of each other. They're daggers of each other. E alpha, E minus alpha, and this combination of Cartans. This particular linear combination. Alpha dot h divided by alpha square. As you say, alpha dot h. Just alpha dot h. Excellent. So that's nice. So what? So what is the following? You see, since we don't know all the algebras, but we know SU2 really well. We know SU2 really well because we've studied about it forever. Okay? So we know the representations of SU2. Now, one property of the representations of SU2 is the following, that if I keep applying J plus, there will be a point where I apply the next one and I get 0. Similarly, if I keep applying J minus, there will be a point where the next time I apply it will give me 0. Okay? So let us suppose, I'll use this guy's notation, so PQ, yeah. Jz was this, right? So we have the Jz value of this is alpha dot hi, alpha dot lambda I. Okay, so I suppose I was acting on a particular state. The hi values were lambda I. So I start with alpha dot lambda I divided by mod alpha square. And I act with E alpha, let's say P times. But E alpha was just J plus, as far as this is concerned. So each time I act with E alpha, it raises J plus by 1. So I get plus P is equal to 0. What does this mean? What is this P? It is some positive integer. More precisely, some non-negative integer. Fine, you're right. Plus 1 would have been. Yeah, you're right. Okay, it will be more useful, as you say, more useful to define this. P plus 1 is 0. And therefore, alpha dot lambda I by mod alpha squared is equal, plus P will be equal to J. But fine, yeah, let's do this. Okay, where J is some half integer. Okay. Then we will have we do the reverse thing. We act with alpha minus q times and go to the lowest weight state. Okay, so alpha dot lambda divided by mod alpha squared minus q, let's say, is equal to minus j. Okay, great. Now, let's add these two equations. We add these two equations so we can get rid of this j. Yeah, we add the two equations so we get rid of j. So we get alpha dot lambda by mod alpha squared plus p is equal to, with this is minus j. Let's see, what am I doing wrong? Plus. Yeah, so if we get this plus this, I'm adding left hand sides. So this plus p plus alpha dot lambda divided by mod alpha squared minus q is equal to 0. Just by adding. And so we conclude that 2 times alpha dot lambda divided by mod alpha square is equal to q minus p. Okay. Now, we don't know much about this q minus p except for the fact that both q and p were integers. Q might be larger than p, in which case it's positive integer. Q might be smaller than p, in which case it's negative integer. But either way, these guys are integers. So this tells us something immediately very useful about all possible representations. All possible representations, the weights, lambda, all allowed weights lie on some lattice. They lie on some lattice, and in fact, we sometimes will define the following notation. Alpha I, like this, is equal to alpha I, 2 alpha I by mod alpha square. Just some notation, right? Instead of alpha I use this, some rescaled version of alpha I. Okay? This here can be written in the form alpha I v dot lambda. So alpha dot lambda, alpha v dot lambda. This is equal to q minus p. Okay? Now these alphas are some particular numbers. We'll come back to a little bit more to this. But it's clear that this quantity here tells you that these weights, all allowed weights of all possible representations, lie on a lattice. What does it mean? What does it mean that it lies on a lattice? It means that if you've got an allowed weight and you take an integer and you add to it another allowed weight with some integer coefficients, that's also an allowed weight. Okay? And that will be true because this is an integer. The thing you added also has this dot product, an integer, and you take integer linear combinations. Okay, so the quantity, the set of lambdas such that alpha dot lambda is an integer defines a lattice. Okay? The set of lambda such that alpha dot of lambda defines a lattice, and so we already see something very nice about weights, that they lie on a particular universal lattice determined just by the Lie algebra. Okay, great. We come back to this equation as we move along. Now, there is one more thing I wanted to say about. There is one more thing I wanted to say about roots. Okay, I want to define this idea called simple roots. As we've already seen, the number of roots is in general much larger than the number of Cartan elements. Like roughly n square minus 1 by 2, if you count only the positive guys, in the case of SUN compared to n minus 1, can be much larger if n is larger than 1. Okay, but we've also seen that the various roots have weights, have alphas that are linear combinations of each other. Because you take alpha 1 with alpha 2, and you get a third, you could get a third one with a weight alpha 1 plus alpha 2. Okay. So what we want to do is to look for a basis in the space of alphas such that we have the smallest alphas in that basis, and all other roots can be built as positive linear coefficients, all other positive roots. I'll tell you what that means in a minute. But intuitively, we want to find a basis in space. We want to find some special roots such that all other roots can be built as positive linear combinations of these special roots. Okay, this is our goal. Okay, now in order to give this thing meaning, actually we will, when we discuss the Weil group, we will prove that some of these things that we're talking about are independent of basis, independent of how we define this positivity. Okay, so what I'm going to do is just define a very crude notion of positivity. I take my Cartans and I put them in some order. R is the rank. Doesn't matter what order I choose. We will see that as we go along. Okay? And then I give a definition of ordering. And there's no natural ordering in a space of n tuples. I just invent one. I invent an ordering that is sometimes called dictionary ordering. And the ordering goes this way. Suppose I've got one set of roots which is h1 to hr, and another set of roots h1 tilde, h2 tilde, up to hr tilde. I just define that this is greater than this if h1 is greater than h2, or if h1 equals h2, sorry, 1 tilde. Or if h1 equals h1 tilde and h2 equals h2 tilde, greater than h2 tilde. Or if h1 equals h1 tilde, h2 equals h2 tilde, h3 equals h3 tilde. Sorry, h3 greater than h3 tilde, and so on.
These HIs are non-Cartan.
Are the Cartans?
These are the eigenvalues of the...
Yes. So I should have said maybe lambda 1 and lambda 1 and lambda tilde, lambda and lambda. They're different eigenvalues. Weights. Exactly, weights. I should maybe have said lambdas. Okay? Why is it called dictionary ordering? Well, if you think, words in a dictionary are organized in the same way. Something is after, one word is after another if the first letter is after that, or if the first letters are equal if the second letter is after, so on. Okay? So we're giving this dictionary ordering definition of greater than to Lie algebras. Now this may seem extremely unsatisfactory because it's extremely arbitrary.
Choose of the dictionary.
Yeah, well, you've chosen a basis, you've chosen an ordering in the basis, and then you choose this dictionary ordering. And of course, anything that we deduce out of this, we're going to have to eventually argue. Then you would have got the same answer for anything invariant from any ordering. This can be done, and we'll see some hints of that later on. So with that assurance in mind, we'll just adopt this ordering. Okay? So now this definition. With this definition in mind, now we can ask, when are given any two roots, we can first ask whether root is positive or not. Because is it greater than 0 root or not? Okay. Second, we can ask, are there some minimal roots? Okay. Now, the set of R smallest positive roots. By smallest I mean least with this set of ordering is called simple roots. Okay, R is the rank. Okay. Now roots in particular lie in the weight lattice. All other roots, the weight lattice is an r-dimensional lattice because you're specifying the charges. It's a lattice built in r dimensions because of specifying the Cartan charges. Okay? So the roots lie in this weight lattice. All roots are linear combinations of the smallest weights or minus of them. Because we know that once we've got the smallest guys, you can build up all the other roots by commutation relations of these guys. Okay? Therefore, what we have concluded is that all roots, all positive roots are positive linear combinations of the simple roots. And then of course there are the daggers of these, which are negative linear combinations of the simple roots. Okay? So a general root is, any general root is sum over I, alpha I mi, where m is some integer. Okay? Excellent.
I runs from 1 to R.
What? 1 to R.
Number of simple
Can you
roots will.
understand why there is exactly rank R number of simple roots? Why?
Well, it seems generic, right? One can prove, but it seems generic because you're trying to make elements on an r-dimensional lattice. So you need
R-dimensional.
r basis vectors,
R weight basis.
right?
I see.
It's just that, really. Okay. Okay, great. Now, we will maybe come to that in a minute, but okay, fine. There's this thing called the largest root. Okay, let me talk about that for a minute. Yeah, something that will at some point be of interest to us is this object theta, which is the largest root. Okay? With this dictionary ordering, it is the root which has the highest integers mi, by highest with the sense of ordering. Okay? And the so if I write theta in particular, it's got some ni alpha I, because that's true of every root, so in particular it's true of theta. For the largest root, these guys have a name. They're called the marks. The Coxeter, exactly. The marks of, yeah, the marks of this group, and they're denoted by AI. AI is very bad notation because you don't tend to think that AI is an integer, but yeah, but these AIs are integers. Okay?
Any AI could be.
Yeah, could be zero.
And these AIs are all are largest.
No, this,
Some AI should be.
yes, this is largest in the sense of dictionary ordering. I mean, of all the roots, okay, of all the roots, this, wait, is it, just a minute. Maybe it's the sum over, just a minute. Let's see. Yeah, I think you're right. The sum over m. Sorry, not in dictionary ordering. In the sense that you take sum over mi, you're right. The sum over mi, and that sum is the largest possible number. Okay. Now, once again, it looks sort of really arbitrary, right? Because it seems very basis dependent and so on. So once again, we will have to work, check that these things are independent. At least some of these things are independent of basis. We will come back to this when we discuss while group. Yes.
This largest root that you are saying, so it will have all these eigenvalues for these R elements, right? And you are saying that all these R elements are maximum. Is that what you're saying?
No. So see, the eigenvalues, as you say, are just, so the eigenvalue under Hm will be sum over m, alpha I m.
One is the rank index and
This is the which root index, and this would be sum over I. Okay, so, and this is mi. Thank you, mi. Okay, that is what Hm is for this guy. But what we're maximizing is not this, it's the sum over these mi's. Okay, we've made a choice of basis for these simple roots, and then the integer linear combinations of the simple roots, those guys are being maximized. The sum of those, the coefficients, sum of coefficients, yes.
Maximizing the root space.
Sum of coefficients in this, sum of coefficients in this particular choice of basis for the root lattice, yeah. Excellent.
No, I couldn't understand this. Can
You choose some, we've chosen our basis vectors, these are simple roots. Now, any root can be written as an integer linear combination of these basis vectors. Now, whatever these integers are, for the ith root, we call that mi.
simple.
Ith simple root, we call that mi, and we sum mi, I from 1 to r.
And all these mi's are the largest.
No, the sum is the largest.
Sum is a vector, right?
Sum is a number.
Sum over mi.
Oh, sorry. Sum over m.
Not
Okay, that sum has to be the maximum. Okay, that will play some role as we go along. Okay, excellent, excellent. Okay, we come back to this largest root in a bit. We need to define various more structures. I know it's getting very boring. I'm sorry. Maybe we should skip. Okay, I know it's getting boring. Hang on for 3 lectures, maybe. Okay. 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 Fine. There is something else that is very important in the study of this group theory. Good.
Is the sum also basis invariant, or the fact that this is the largest?
Yeah. What is will be basis invariant is this sum. In fact, the sum, because this sum, yes, the sum is basis invariant, and that quantity is called this Coxeter number. Okay. Yeah, that quantity plus 1 is called the Coxeter number, and that is a characterization of the group. Yeah, so that sum is some basis invariant thing. Okay, excellent. We're now moving to define the Cartan matrix. Okay, so let's go back to this equation. This equation here, okay, told us that alpha dot lambda divided by mod alpha squared times 2 was q minus p, some integer. Now this was true for every weight. In particular, it's true for a root. Okay, so let's do this. Let's say that 2 alpha I dot alpha j divided by mod alpha j square. J is a which root index. Okay, so these roots are themselves vectors, but ith, jth root. This thing is, some q minus p. Particularly in the adjoint representation. Okay, exactly, particularly in the adjoint representation. But there is something else that we can say immediately. That something else is this. That something else is that there is no. I want to argue that the value of q. I want to argue that in this case, q is equal to 0. Okay, which means I want to argue that by acting on the weight of the jth root with the ith lowering operator, I get 0. These are the simple roots. Okay. Now, you see, suppose I could act on the jth simple root, alpha j, and lower it. Okay, suppose I could act on that, lower it and get another positive root. Then that positive root would have had weight alpha j minus alpha I. Okay? Had it been that this was some positive root, okay, had it been that this was some positive root, but then this plus alpha I would be equal to alpha j. But we have assumed that alpha I and alpha j are both simple roots. Okay, so if this this plus this alpha I is alpha j, and had this been a positive root, okay, that would contradict that they were simple roots. Okay, so now why is this? What I can do is do this in the space of i's. In the space of i's, I can choose this guy to be larger than that guy. Let me choose j to be a larger root than I. Then alpha j minus alpha I is a positive root. Okay, so if I make that choice that j is the larger root than I, then I've got two positive roots. Sum of these two positive roots gives me alpha, and that's a contradiction. Okay, and therefore we conclude that with this choice at least, that this j is larger than I, this q has to be equal to 0, because you cannot further lower, right? You lower one more and you get 0. Okay, and so we get 2 alpha I dot alpha j divided by alpha j square is equal to minus p. Now, what have we learned from this? One of the things we've learned is that these alpha I dot alpha j's, their dot product is negative. Now, if alpha I dot alpha j is negative, it's alpha j dot alpha I is also negative. So this choice I made was saying j was larger than I was convenient, but it's true for just any pair of simple roots. Is this clear? Okay. This quantity is called, people give it a name, this alpha, they call this guy Aij. And let me check that they're dividing by j square. Yes, it's called the Cartan matrix. Okay, so it's an R cross R matrix. The matrix of dot products of simple roots divided by Aj square. Note it's not a symmetric matrix. Note it's not in general a symmetric matrix. We will see as we go on that some groups have the property that all of their roots and certainly all of their simple roots have the same length. Simply less Lie algebras, exactly. So in that case, this will turn out to be a symmetric matrix. Okay, you remember we had defined this alpha, this dual sort of root. So Aij, if you just look at those two definitions, the same as alpha I dot alpha j dual. Okay, and this is equal to minus p. Okay, so this is called the Cartan matrix and characterizes, as you see, this Aij, characterizes something about the geometry of the various simple roots. Because it tells you that in this d-dimensional space, what the angles are between the various simple roots. Okay, let's see a little bit more about this object. Let's take this Aij and multiply it by Aji. No sum. Huh? I just take Aij and I multiply it by Aji. Please. No, I'm writing it now in general. Okay. The fact that alpha I dot alpha j was negative, we deduced from writing it, from taking that case, but I'm writing it in general. Okay, so since it was negative, it was negative. Didn't matter. Yeah, go on.
These alphas are simple roots. Are they simple?
Yes, simple roots.
But if they're simple roots are defined in a way that they're positive. Right?
They're positive, which means that these numbers that in terms of dictionary ordering they're positive. It's true.
Yeah. Yeah.
Okay, it's true, but you see, this positivity is not saying positive in every direction. It could be positive in the first direction, then you could be negative in the other direction. Right, but that's our definition of positive. As long as you're positive in the first direction, you're positive. If you're 0 in the first direction, then you have to be positive in the second direction. So this positivity does not forbid. It's not like a cone kind of positivity, which I think is what you have in mind. It's not like every coefficient was positive. If every coefficient had been positive, then the dot products would necessarily have been positive. But that's not the case here. And in fact, we're seeing it's never the case. Because the dot products are always 0 or negative. Is this clear? Okay, excellent, but good question. Okay, so let's take this. We can have a vote at the end of this class. If you want to just skip on to the physics, we can also do that. And everyone's looking very bored, even I'm feeling very bored. But okay, let's go on at least. Yeah. Okay. We have let's consider this quantity alpha ij, alpha ji. Okay, emphasize we're not summing. So what is this quantity? Well, it's 2 alpha I dot alpha j, the whole thing square, divided by mod alpha I square mod alpha j square, and then there's 2 squared, so it's 4. But Cauchy-Schwarz inequality tells us that this quantity is less than equal to 1. So this quantity is less than equal to 4. Clear? Okay, so these Aij's have the property that Aij times Aji is less than equal to 4. We've already seen that these Aij's are negative integers. Okay, so now what are the possibilities? Well, first we could have Aij equals 1. First, of course, we could have Aij equals 0, and then that will tell us that Aji is equal to 0, because the only way Aij can be 0 is if alpha I dot alpha j is 0, and that's true. So we could have Aij equals Aji is equal to Aij is equal to 0. This is possible. Okay. Now we could have Aij equals 1. Minus 1, always negative. We could have Aij is equal to minus 1, in which case what would be allowed? What would be allowed is Aji is equal to minus 1, minus 2 or minus 3. What? Minus 4 also. Minus 4 also. But okay, you see this equality will only work if the two roots are collinear. And no non-linear, non-equal. Yeah, if I not equal to j, that it's less than. Yeah. So let's take I not equal to j, and then these are the possibilities. Okay. Now what if Aij was equal to 2 or minus 2? Well, Aji could be 1, could be minus 1, but that's it. Because minus 2 would hit the bound. Okay? So what we see is that it's never possible for all Aij's to be greater in modulus than minus 1. At least one of the Aij's, we've got an exhaustive listing of possibilities, has to be minus 1 or 0. Then all the non-zero ones. There has to be at least one minus 1. Now let's look at the difference between Aij and Aj. The difference comes, the ratio is the ratio of norm squares of I square and J square. But we see from this classification here that what are the possible ratios? The ratios, at least for the ones with non-zero dot product, for squared norms are 1, 2, and 3. Because you could have 1, 1, you could have 1, 2, or you could have 1, 3. That's it. Okay? So we've already seen an important result, or at least started seeing. We've not really seen it for the guys which have zero relative dot product. That requires more proof. But it's a general fact about Lie algebras that the roots in every Lie algebra, either they are in the ratio, the ratios are 1:2 or 1:3. And that sort of is consistent with the analysis. We've not exactly shown it. Okay. There are long roots and short roots. Some Lie algebras have all roots of the same sign. These are the simply laced Lie algebras. But there are some roots, Lie algebras that are not. Oh, we have to soon go. We'll really speed up next time. I'm sorry. Okay. Yeah. Some Lie algebras have. Yeah. We have to go. Yeah. With these ratios of fluids. Okay. Are these? Okay. This Cartan matrix characterizes the angles, as we said, between various roots. And these angles, as you see, because the dot products are always negative or 0, are either 90 degrees or some very particular values. Actually, it's like 120, 150, and so on. We'll come back to that later. Let's stop now. Okay. Yeah. Okay. My plan at the moment is next lecture I will try my best to complete our discussion of ordinary Lie algebras. I can speed up if you think I'm going too slow. Speed up. Excellent. Is this a consensus view? No. Okay. Okay, we'll see. But we'll try to finish our discussion of Lie algebras next class so that the subsequent class we can get to new things. All of this in some language you guys know, right? I'm just reminding you. But, okay, come.